Right. Welcome back. I'm glad you all came at 9 o'clock and not 10 o'clock like it said on the syllabus. Sorry, I hope nobody's going to show up at 10. I'll say it must be that daylight savings. That'll be hilarious. Okay, we were talking, we just sort of got started with some basic terminology last time, so I will remind us that we're talking about languages. So an alphabet is something that's, usually we write the capital sigma for the alphabet, and the alphabet consists of some finite number of individual symbols. So it's often we're going to use an alphabet like ABC, or something like 01 is another common one that is used, in this class. This is the alphabet. It's just some finite set of individual symbols. And then a language is a specific set of strings taken from that alphabet. So a language is a set of strings taken from the alphabet. And a string, remember, means like not an individual letter, but some kind of sequence of letters all jammed together. So a language is a set of strings taken from some alphabet. So for example, for the alphabet, if I'm using the alphabet, say 01, something like the set of all, I think I wrote this at the end last time. This is a language. These are weird words to use. I mean, language really just means a set. It's a set of strings. All right, but we call it a language by analogy with real-world programming languages and also like spoken languages, which are similar. All right, so that is a language. Can I just say a few little technical details? So this N here means the set of natural numbers. And there's always a bit of ambiguity. Some people think that N should include 0 as the starting number, 0, 1, 2, 3. Some people start N with 1, 2, 3. In this course, because of our textbook, this is the way that they always do it in our textbook. N starts with 0. This you just have to get used to in mathematical context, knowing whether N is supposed to start with 0 or 1. I taught a course last semester where I used N all the time and always started at 1. Sorry for any confusion. In this class, the N is always going to start with 0. So this is the set of natural numbers. All right, that's a language. This language you could describe in words as the set of all strings which begin and end with a 0 and have a bunch of 1s in the middle. All right. If you wanted to write, say, the language of, how about just all strings which begin with 0, you could write it this way, something like this, 0x, such that x is a string, right? This would be any string which starts with 0 and then has something else afterwards, all right? So that is also a language, all right? Languages are typically going to be language, I wrote. Languages are typically going to be infinite, like these two sets here are both infinite sets, meaning there are infinitely many different strings of that format and also infinitely many different strings of that format. All right, this is what a language is. Also, this is kind of stupid, but the empty set, this counts as a language also. A language is just any set of strings, and it could be empty, right? So this is also a language. Not terribly interesting, but it counts as a language, all right? That is actually the smallest possible language that there is, right? Because any language is just a set. So that's the smallest possible language there is. What's the biggest possible language that there is? Well, a language is a set of strings. So the biggest one you could take would be just like this set, which contains every string. And that is similarly kind of useless because a language in which every string is sort of a legal word is not a very interesting language. Like ordinary languages are not like that. Not everything is a real word, right? If everything was a real word, you wouldn't really be able to communicate very well. So anyway, that's the other sort of the biggest possible language. We are actually going to talk about it often, though. The biggest language, sorry, too early in the morning to write the word language. The biggest language is the set of all strings. Not very interesting on its own, but as happens often in mathematics, like the stupid examples are things that you talk about all the time, like the number 0 or something like that. The set of all strings on your alphabet sigma, and this is written, there's a special notation for this, sigma star. So sigma star means the set of all strings you can make using letters from sigma. All right? And there's a name for this actually, although I'm usually just going to call it sigma star, but although this is named after somebody. This is called the Kleene closure. Kleene is a guy's name. The Kleene closure of sigma. All right, it's just all possible strings that you can get for some alphabet sigma. All right, so actually this language right here is more typically we would write it this way: 0x such that x is in sigma star. What that means is this is all strings that look like 0 followed by something. And what is the something? The something is anything, right? It's the same as what I wrote up here, although we're typically going to write it more in this way. So actually, we will use the sigma star all the time, not really by itself, but as a part of other things. It's a useful kind of way to write things. So this means the set of all strings that look like 0 followed by something, and that something can be any other string. All right, it's the same as what I wrote up there, just in words. All right, I want to explain a little bit of the terminology of language is meant to be kind of and make an analogy between this and actual real world, either programming languages or spoken languages. A language, so let's talk about like a natural language, a spoken language. In this setting, you could think of a language as like the English language, for example. You could think of, if you ask yourself sort of, what really is the English language on a deeper level? This is kind of like a stoner question. If you're sitting around with your bros thinking about, yeah, man, like what really is language, you know what I mean? One way to answer that question is like, the English language is a set of allowable words. And those words are the English language. Actually, it's a little more useful way to frame it slightly differently. I'm going to say a spoken language, first of all, has an alphabet. And the language itself is the set of all, I'm going to say allowable, not words, actually it's more useful to think of it as the set of all allowable sentences. By allowable, I mean like grammatically correct. Now, real spoken languages are kind of fuzzy in that people, when they talk, often violate so-called rules of grammar, and it still works as a language. So there's some controversy among linguists about whether rules of grammar are even a real thing at all, but I don't want to get into that. Let's just pretend that spoken languages have actual rules and there are certain sentences which are allowed and certain which are not. So the language is the set of all allowable sentences. So for example, the English language you could think of as having the alphabet A, B, C, etc. down to Z. And then also, in order to make this work, what I'm trying to describe, you also need a space, which I'm writing like a underscore there. The space has to be allowed to make a legal sentence in English because you need words to be separated. Although there are some, I recently learned, I believe in the Thai language, they don't write spaces in between words. Anybody know Thai? I think you write an entire sentence just all jammed together, and then they don't use spaces in between words. But anyway, in English we use spaces in between words. And then, so that's the alphabet which is required to make an English sentence. Let's leave out punctuation and capitals or whatever. And then I'm going to write the English language. Let's write this with a fancy big E. And then you can say something like, the sentence, I have a dog. This is an element of the language E, meaning that that is a legal sentence in English. Whereas something like, I have a dog, this is not a legal sentence in English because that is not a word, that second thing that I wrote there. Or something like, I have. This is also not in English. This is not an element of the language because that string doesn't make any sense in the English language. All right. This is the analogy that is made. This is why those sets of strings are called language. So in this point of view, the English language consists of all possible strings that make legal, grammatically correct English sentences. They don't really have to be, I'm not talking about sentences which are true or false. I'm just saying they are legal grammatical sentences. All right. We can also think of this in the context of programming languages. So a programming language, similarly, is all, I will say, giant strings, usually giant, which make legal programs. And in most programming languages, there actually are real rules about what is a legal program and what is not. What I mean by legal is like when you write a program, say in Python, and try to run it, it actually doesn't give you an error. Like it actually does something. All right. It doesn't have to do something useful, but it's just a legal program. All right. When you do this in most languages, most programming languages, you have something like a compiler or an interpreter that you run your code through, and I will say the interpreter or the compiler or whatever acts first and foremost, like before it even does what your program is instructing it to do, it checks to make sure that your program is valid. Or sometimes it checks as it goes. But anyway, the programmer acts as a, I will say, validity checker. Right? The interpreter, I mean. Did I say? I don't know what I said. The interpreter acts first and foremost as a validity checker. It checks to see if your program makes any sense at all. And if it does make sense, then it tries to do whatever you said to do. And this is actually the first kind of machine that we're going to be talking about. So as we go through the course, we're going to talk about different types of computing machines and sort of increasing complexity. And the very first type of machine that we're going to talk about is just one which looks at a string and it tells you whether or not that string is legal according to some rule, depending on what language you want to talk about. So we're going to talk about a simple machine and the terminology we're going to use is either accept or reject strings. So this is you could think of this like a computer which doesn't really actually do anything, but it just reads a string and tells you if that string is legal or not. It is either accepted or rejected. All right? And the simplest kind of such a machine, actually we're going to talk about several machines of that general type, but the simplest kind that we're going to talk about is called, this is what, we're going to be talking about this for the next week or so, at least. The deterministic finite automaton. The deterministic finite automaton. And we're pretty much always going to write DFA for this. DFA means deterministic finite automaton. So each of those words, what they mean, first of all, the word deterministic. Anybody seen this before? How would you describe the meaning of that word? Is it too early to discuss the word deterministic? don't know, maybe you haven't heard this word before. This basically means it is a machine which has no randomness to it. Deterministic means that the output, whatever the behavior of the machine is precisely determined by the string and nothing else. So this machine, it just does what it does, regardless. It doesn't make random choices on its own. So this is very simply, I would say, no randomness. If you want to say a little bit more specifically, this has the same behavior. I started this sentence badly. I wanted to say the machine, it responds the same way to the same input. So if you give it the same input twice, it's going to do the same thing twice. It's not going to just like randomly decide to act differently the second time around. So I will say the same input always gives the same result. This is how a computing machine typically works, unless your machine is meant to have some kind of randomness in it. But the DFA always is deterministic. And then finite. Finite means that the machine kind of has something like a memory, but it's only finite. It can only exist in finitely many configurations. And this also is like your computer, although your computer has the possible number of configurations that your computer can exist in is very, very, very large, but it's still technically finite. But anyway, finite means the machine has only finitely many possible configurations, and we're going to call these states, all right? The machine can only be in finitely many different states. Like a light bulb has two possible states. It can be on or off. Your computer has many, many possible states that it could be in, but it is technically finite just because your computer has a finite amount of RAM in it or whatever, and there are technically only finitely many configurations it can be in. And then this word automaton just kind of means like a machine. I mean, often this word is used as a fancy word that means like robot or something. Although this is not a walking and talking robot, but we will use this. A lot of, this course, the Theory of Computation, is something that exists at most universities, and often this course is called automata theory. So it's the automaton is a word that is often used. All right. Anyway, I want to do for the rest of today a bunch of examples of specific DFAs that do specific things. All right, so let's try. I'm going to try and describe an example of what a DFA looks like and sort of what the capabilities are. Let's talk about an even length machine. All right, this is a very simple example of a DFA. So on the alphabet that I'm going to talk about this time is just strings of a single letter, A. All right, so in this alphabet, a string could look like, well, it could be the empty string, or it could be just A, or it could be AA, or it could be AAA, or AAAA, right? Those are what the strings look like, just a bunch of A's. And I want to make, so we'll make a DFA, which, remember, the purpose of a DFA is to read a string and either accept or reject. And this particular DFA, I want to make it so that it reads the string and accepts if the length is even, and rejects if the length is odd. All right. And the way that a DFA always works is you give it the string, the DFA reads the string one letter at a time, and then by the time it gets to the end, it tells you the answer, either accepted or rejected. So a DFA reads the string one letter at a time, left to right. Left to right. And after each letter, it might change its internal configuration, what we call the state. So you read the first A, and then maybe change to another state if you think the state will sort of keep track. Do you think this thing is even or odd as it's going? Because that's what the machine is trying to decide, whether the string has even or odd length. So the DFA reads the string one letter at a time, left to right, and after each letter maybe changes state. It doesn't have to. I mean, in general, a DFA can decide to change state depending on what the letter was, and maybe it'll stay the same state. So after each letter, maybe changes state. And then at the end of the string, it either accepts or rejects. All right? Depending on, well, in this example that I'm trying to do here, it wants to accept if the string is even length and reject if the string is odd length. All right? If you think about it, you can imagine such a process working with basically two states in this example. The two states keep track of, have I seen an even number so far, or have I seen an odd number so far? If you've seen an even number so far, but then you see one more letter, then you say, okay, I guess it's odd now. And then if you see another letter, you say, oh, okay, I guess it's actually even now. And you keep on flipping back and forth. And by the time you get to the end of the string, if you end up in like the even side, then you say the string was even. If you end up in the odd side, you say the string was odd. So this is how I'm going to indicate all those words that I just said are actually very easy to write in a diagram. And this is why I said you probably shouldn't try to type your notes for this class, because there's going to be a lot of diagrams that look like this. What I have here is a diagram of two states. These are the two states of the machine. And if you like, you can give little like labels to the states if you want to. We're not always going to do this, but just for myself and all of you folks here, I'm going to say the one on the left represents the state where I think the string is even so far, and the one on the right represents the state where actually I think the string is odd. And the way I describe the way that this machine is supposed to work is, if you're in the even configuration and you see one more letter, then actually you should switch over to the odd. And the way that you indicate that is like this. This is an arrow that's labeled with the letter A. That means, so the meaning of this arrow right here is, if I'm in the even state and I read 1A, then switch to the odd state. Right? So that arrow has a little A on it, because this is what you should do if you see the letter A. Now, in this example, the letter A is the only letter possible. So, but in other examples, you might have some letters labeled with A's, some with B's, or zeros and ones, or whatever. All right? Let's think about from the odd state. You have to say from each of these states, what happens if you see an A in the odd state? Where should the arrow go? You have two choices. You could say the arrow goes back here, or you could say the arrow goes back here. You have to think about what this machine is supposed to do. Which one is it? Should it go back to the other side or stay where it is? Back to the other side, yeah. Like I said, if you think the string is even so far, but then you see one more letter, you go over to the odd. And if you think it's odd so far and you see one more letter, you go back to the even. So it should be the one that goes back to the other side. And this also I label with an A. That means if I'm in the odd state and I see the letter A, I should switch back to the even state. All right? And then by the time I get to the end, well, just like whichever state I end up in, that's the one that the string actually was, right? If I end up in the even state, then the string actually must have been even length. And if I end up in the odd state, the string must have been odd length. And that's how you decide whether you accept or reject. Now, I said we should accept an even length string, and the way we indicate that on the diagram is like this. This circle gets sort of like a double super double outline. All right. So in this case, let me just say some transitions or some terminology here. The arrows are called transitions because each arrow represents the machine sees something and decides to change to a different state. So the arrow are called the transitions. A circle like that versus a circle like this. So a circle with only one outline, this is called a rejecting state. And a circle with two outlines is called an accepting state. So that means if your machine ends up in a rejecting state, then the final answer is the string is rejected. And if this machine ends up in the accepting state, then the final answer is that the string is accepted. There's one more detail that needs to be included in this machine, and that is where should you start? Which of those two sides should you start on when you begin the computation? So before you've looked at any of the letters, can anybody say, in order for this to work out, which one should we start in? What do you think?
Even.
Yeah, the even state is where you want to start. It's because if you start from nothing, you kind of think like, okay, nothing is sort of like length 0. And that counts as even, right? And then the first thing that you see should move you over to the odd because that would be length 1. So I should start in the even state, and the way I indicate that on the diagram is like that. Sort of an arrow from nowhere means that's the one where you start. So this arrow here indicates the starting state. All right? Anyway, this is the DFA, which decides whether a string is even length or odd length. It has two states, and it just goes back and forth. So it's, I'm just going to draw that DFA again. Like this, right? Those labels I wrote even, odd, those are really just kind of comments for myself to help me think about the machine. But the machine itself you don't need to put labels on it if you don't want to. The meaning of this is, well, I imagine this one represents even strings, this one represents odd strings. Okay? Anyway, to evaluate a string, just follow the arrows, right? And that tells you if it's accepted or rejected. So for example, AAA, what do? You have to watch my little red dot. AAA, you always start here, and then I read the letters one at a time and follow the arrows. I go A, and then I end up here, which means the string is rejected, which it should be because it's odd, right? So this is rejected. Whereas something like A, on the diagram, I start here, I go A, and I end up back here, which is the accepting state, and so this is accepted. This is how a DFA works, etc., right? And this one actually does do what we wanted it to do. It accepts all even lengths, and it rejects all odd lengths. What about, you can even do the empty string. Remember the lowercase little epsilon there means the empty string. So to read the empty string, we start here because this is the starting state, and we do nothing, and it is accepted because I ended up here after doing nothing. Doing nothing is what you're supposed to do here. This is accepted. Which it should be actually because that string, the empty string has length 0, and 0 is even. So it should be accepted, and it was accepted. All right? Any thoughts about that? This is our sort of, baby's first DFA. It really works. So a typical homework problem would be something like, I describe to you a language, and then you create a DFA which accepts that language. This one accepts the language of strings which have even length. Remember, when I say language, I just mean set. So this the set of all strings with even length. All right? Let's try some more. We got 20 minutes more here. I got 2 more examples, and then I had some for you all to try. You will find that this takes a bit of getting used to. Creating these little diagrams is really very similar to writing computer programs in a new language, although this doesn't look like a programming language. So you'll have to kind of learn to train your mind a little bit. How about this? here's a new example on this alphabet. A's and B's, make a DFA to accept any string with no B's. All right. So this is going to be a DFA which, if it's all A's, it should be accepted. If it has any B's anywhere, it should be rejected. All right. This one is completely different from the even and odd thing, but because, and like I said, it's going to take a bit of getting used to formulating. You have to learn how to sort of think like a DFA. But I can do this one also in two states. And the two states which matter in this case is, as you've read the string so far, did you see any B's or did you not see any B's? If you have seen B's, it should be rejected. And if you have not seen any B's, it should be accepted. So I'm going to make my two states. And I'm going to, just to emphasize what I just said, I'm going to, let's say the one on the left is the state which represents a string where I've not seen any B's yet. And this one over here is a string with some B's. All right? And can I say this state, well, I'll say in a moment. These are the two states. What should the arrows look like? So let's think about, if I'm over here, that is, the string that I've read so far has no B's anywhere in it. What if I see an A at this point? Should the A stay in this configuration? Or if I see an A, should it make me go over here? What do you think? Yeah, it should stay here. If I've never seen any B's so far, and I see an A, well, still then I have never seen any B's so far. So I'm going to put the A arrow like that. This means if you've never seen B's yet and you see an A, then still you've never seen B's. But if I see a B from this state, then I should go over here, right? So this DFA looks pretty different from our previous one. Each state needs to have two outgoing arrows, one with an A and one with a B, that tells you what to do from this state if you see an A and what to do if you see a B. So what about over here? I need to make two arrows here, one with an A, one with a B. So if I have seen some B's already, and then I see another A, then should I go back to here, which means I've never seen any B's, or should I stay over here? I think the answer is stay over here. Over here represents I have already seen some B's. If I see another A, well, it's still true that I've already seen some B's. So, like that. If you've seen B's, you've seen B's, whether you see an A or not. Am I right? I've seen some B's in my day. What about a B? If you're over here, you have seen some B's already, and you see another B, what do you say? Also stay over here. So you can write another arrow, but they will look at you funny. Typically, the way we do that is like this. So if you see an A or a B, then you stay on that side. And this is the whole DFA, all right? Now, we need to also indicate where is the starting state and also which of these two states should be accepting. Can anybody say which one is the starting state? Yeah?
The left one?
The one on the left, yeah. You should begin sort of from a clean slate. You have not seen any B's yet. So that's the starting state. And then, which one should be accepting? Remember what I said here. It should accept any string with no B's. So I think this one should be the accepting state also. All right, great. This is my DFA. All right. There's a, I hope that this makes sense to everybody. There's a sort of useful pattern that you're going to use in a lot of your DFAs when you create them that you can see right here. What we have right here is what you might call a, can I just make a little comment about that part of the diagram at least? This is a permanent rejection state. I've been there, am I right? Once you go over there, it's going to reject no matter what. All right. So actually, I think that's a very nice way to think about this DFA. It is, you start off accepting. As long as you see A's, you're still accepting. But if you ever see a B, it's rejected no matter what. All right. This is a permanent rejection state. It is a rejecting state which is inescapable. Right. Once you go here, you stay here forever. Okay. I got one more example, and then, like I said, I have some for you all to try. How about a DFA, one more. A DFA which, on the same alphabet, A's and B's. That's the alphabet, which accepts any string. I'm going to try and sort of combine the two. Any string with an even number of A's and no B's. All right? This is kind of a combination of the two previous examples. I want to accept an even number of A's and also no B's. All right? My strategy here is basically I'm going to copy this even odds kind of structure with the A's, but at the same time I'm going to make it sort of permanently reject if you ever see any B, all right? Because it has to be an even number of A's and never a B. So that's what I'm going to do here. This is going to require 3 states in this case. Sorry to scroll away. I'm going to have 3 states here. The top 2, I'm going to go back and forth with the A's. This keeps track of if the A's are even or odd. All right, so I'm going to go like this, and this is going to be the accepting state. So what I have there is my little even odds machine, and I want to make it so that at any time, if there's a B, the string should be rejected. So that means if I see this state on the bottom, I'm going to make like a permanent rejection. And if I see a B, this is like the failure state. And here I put the loop with the A and the B to make it so that if you ever go to that failure state, it's going to stay a failure forever. All right? This is my DFA which does that. So the only way to get to this accepting state is if there's an even number of A's and never any B's. All right? I left one thing out of my diagram. What do I need that I'm missing? Yeah?
Starting point?
Yeah, the starting point. And what do you think it should be? Somebody else say? Yeah?
The accepting one?
Yeah, it's the one, the accepting state in the corner there. Certainly you wouldn't want to start down here, which is a failure. When you're deciding where the starting point should be, you want to kind of think about what should happen if it was the empty string. Should the empty string really should start off as being it's even length and it has no B's. So that would be this state here. All right. I hope this is beginning to come together. You know, as in many types of math, you really have to just try examples to make sure that you really understand it. So I think we got time to do 2. How about try one which accepts any string starting with A, but then has anything else afterwards. And then try one with any string ending with A. These are two separate examples, and they're going to have to look different. All right. See what you think. I hope you don't mind, I'm going to try and walk around and see how you're doing. I'm not trying to, grade you or evaluate you. I'm trying to be helpful. So if you don't want to talk to me, that's fine. But I will ask you how you're doing, and let me know if you have questions. I'm happy to help out. I'll give it about 5 minutes, and then we'll talk about it, just because we only have about 10 minutes. I gave you a hint for the first one. It should have 2 states. And the starting state in the first one, the starting state should not be an accepting state. That's because you don't get to be accepted unless it starts with an A, right? So you have to actually see that first A before it gets accepted. Because if you see a B, then it's not going to be accepted. So that's my little hint for the first one. Actually, the other state should be accepted. Think about it. Then you need this is pretty good, but there has to be an arrow from here. Sorry, I don't think you can do this with 2 states. You need 3. There. I'm still not telling you what to do. Getting anywhere?
Wait, so the first one requires 3 states?
I think so. This, oh, you're starting with
wait. Yeah. So they could always put an A second and then go here.
Yeah.
So it would have to just be.
Okay. Getting anywhere?
I think so.
I think that should be it.
Yeah.
That would be accepted. How's it going? Mm-hmm. That'd be good. Starting with A, very beginning, and then you see how the doesn't change with that. Get anywhere? Circles. First step. Oh, that's pretty good. You need some arrows. Every state has to have 2 outgoing arrows. Mm-hmm. I like that. Yeah, I meant to see the output.
Oh, just you
All right.
I put that sign to show holes.
Okay. Yeah, I meant for, the alphabet is supposed to be A's and B's. What I meant at least. I'll give you 1 more minute. Sorry, I know not everybody's done, or everybody's not done, perhaps. I don't know. Yeah, this is good. So one problem with this is, this will accept a string that looks like B, I think. So you need to make this go. That's why you need 3 states. How's it going?
Oh, so
Let's get, I think I don't think of this as,
so you plug it in.
this actually in here, and only because you haven't seen any here. So I would say,
You don't have
how's it going? I like this. Remember, every state has to have 2 arrows coming out. So this is what happens. You also need to know.
Yeah.
Yes.
So
Right.
if it's B, it will go to.
Yeah, so I think this should say B.
I'll just do it again.
But now
I
it's
wanted to-
Yeah. Sorry I didn't make it all the way around, but we got to go in a few minutes, so let's talk about these. These, I hope you believe me now when I say these are a little tricky and it takes some getting used to. So if you feel like these are very confusing, don't worry about it. I mean, that's all part of the process. What you should do, so this one, starting with A. Now, I didn't say this clearly, but I should have. The alphabet I want in this case is just A's and B's, right? Any string starting with A should look like this. I start in some state where I don't know yet whether it starts with an A or a B. But if I see A first, I'm going to go over here to the accepting state because I'm supposed to accept when it starts with A. And if I see B first, I'm going to go over here to a rejecting state. And both of these, this one will be sort of a permanent rejection state, like this. So this means if you started off with a B, it should be rejected no matter what happens. And this one means if you start off with an A, it should be accepted no matter what happens. So I'm going to put like this guy here. All right? And that is my final answer. I hope that, I saw some people got something like this as I was walking around. All right, this is a permanent rejection state, and this is a permanent accepting state. And it's based on that first letter. Was it an A or a B? All right? Any questions about that? This is one of those things that looks very simple once you see the answer, but it does take some getting used to get to that point. Okay, and then what about the other one? Any string ending with an A. Let's try that. You want me to get to this one? Actually, I can do this one in two states. There they are, two states. Anybody have an idea? I say? Yeah, what do you think?
I go from the left to the right if it's an A.
Okay.
And then back if it's a B. And then stay at the right state
Whoa,
if it's
sorry.
A.
Yeah, so what are, do you have thoughts about, like, what do these two states represent to you?
The first one is the initial state, and then the second one's the passing state.
Okay, yeah, so this is the accepting state,
Mm-hmm.
and this is the starting state? Yeah.
Yeah. So the right would be ends in A, and the left would be doesn't end in A.
Yeah, right. So this state represents, sorry, I made the circle a little too small to read, but this state represents ends with A. So if at any time you saw A, then at least so far, the A is the last thing you saw. And so you should imagine that your string is ending with an A. And then from here, he said, if you see B at this point, you should go back over here, all right? If you thought the string was ending with an A, but then you see a B, then you say, oh, okay, I guess it wasn't ending with an A because there was a B. The last thing that I read was a B. This is good for the basic structure. There should be some more arrows. What else you got?
Just loop back on the right if it's A, and loop back on the left if it's B.
Yeah, great. So you got to think, if you think the string is ending with A, but then you see another A, well then, yes, it is still ending with A. The last thing I saw was A. So like this, and then he said on the other side, a B like this. That's because if the string did not end with an A, and then you see a B, then still the string does not end with an A. All right? That's how we do it. It's, to me, a little weird that these two answers look so different. I don't know if you were expecting them to be just like one is like the same, only backwards or something. No, actually, it's quite different. The way you have to think about these is a little different. And it takes a lot of practice, which we are about out of time now, but we'll do some more examples of this next time. All right. I said there's a homework every Wednesday and a quiz every Friday, but not today. So our first ones will be next week.